So, hello, if I can have your attention, please. Thank you. Okay, we will have poster pitches. We'll do this exercise 3 times throughout this year's NeSy workshop. It is a fun activity for everyone who doesn't have to pitch themselves, because actually pitching is highly stressful, at least for people like me. You have 1 minute 45. You'll get a 10-second warning at 1 minute 35. At 1 minute 45, your slide will change to the next presenter. There is no time for Q&A. Why? Because that's what your poster is there for. So make it attractive, make it interesting, tease people to come to you and talk to you. There will be plenty of time afterwards. We will go through the pitches in order of appearance on the program. So all of you, this is, if I'm not completely mistaken, the first poster pitch session. Find your name on there and you have a rough idea when you're up. Also, you can clearly distinguish when you're up because you will see your slide. And we start with Maurizio Proietti and Francesca Toni. Your 1 minute 45 starts now.
Hi, everybody. This is a very quick, short paper on a roadmap and a survey on neuro-argumentative machine learning, which is about learning argumentation frameworks. These are symbolic representations from a field called computational argumentation, which is pretty good at resolving conflicts, for example, of the kind emerging when somebody needs to decide whether you are covered or not when you break down in the road. It's also pretty good at supporting reasoning that is non-monotonic when you need to change your mind, when new information is acquired, and is also explainable. So it's a pretty good representation to learn when performing neuro-symbolic learning. Next. What we did is looking at what's out there, what's available in the literature on joining together neural networks and argumentation with the focus on learning some bits, either the neural networks, the argumentation framework, or both. So we looked at 3 challenges to consider in the future, namely that of having a pre-trained neural network from which we can learn an argumentation framework, having an argumentation framework from which we can learn a neural network, and learning both of them together. And I'm done. I'm looking forward to seeing you at the poster.
For reference, Francesca just demonstrated that you can do it in 1 minute 26. Okay.
Hi.
Next one. Your time starts now.
Okay.
Go.
Hi, I'm Kwan. I'm trying to close a Neural-Symbolic cycle. Basically, I'm trying to explain what a black box of a CNN by extracting certain knowledge and then transform that into certain rules so that it's more presentable to medical doctors in a way that I can improve the communication. So there's a human in the loop in this sense, whereby a domain expert can then appreciate what's extracted from the knowledge and give us more relevant information. And also there's an attempt here that I'm trying to improve the learning from this knowledge. And hopefully that by doing this cycle, that is more traceable, is more reasonable to understand what actually is in the model itself. And hopefully that when we deploy these models, we will be able to justify why things are happening well within the model itself.
Thank you. Your time starts now.
Our world is full of constraints which influences our behavior. Next slide, please. For instance, when we are driving a car and we see a pedestrian wants to cross the street, we stop and let the pedestrian cross the street. Next slide, please. Or in a warehouse where all employees maintain minimum distances to ensure safety. Next slide, please. So now, if we want to deploy an autonomous agent in these environments, for instance, a self-driving car or a towing robot in a warehouse, if we want them to be successful, they also need to maintain with these constraints of the environment. Next slide, please. But constraints are often implicit, hard to specify, environment specific, and can also be in conflict with the goal of the agent. So it's very hard to program them manually into the decision making of the agent itself. Next slide, please. For this, we provide a solution by learning these constraints from expert demonstrations and representing them as formal logic. So this representation has the advantage that it is interpretable, so we can get insight into the decision-making of expert agents, but it's also transferable to autonomous agents using already existing safe reinforcement learning frameworks. Thank you.
Your time starts now.
Hi, everyone. In this paper, we present a predicate invention approach for Neural-Symbolic ALP problem to learn relational concepts from visual scenes. Next. Neural-Symbolic system usually refer the logic rules from images. If you see the positive images and negative images, there are rules behind it. Such pattern can be complicated. Please, next. But usually, to recognize these patterns, you require background knowledge. So in our paper, please, next, we present the predicate invention. So we can require less background knowledge and consequently gives much more generalization for solving the logic patterns. The invented predicates are explainable and interpretable based on the first order logic. Next, please. So here are some of the results of the experiment. We show it's capable for solving complex logic patterns in 3D, and it's very efficiency and accuracy in the absence of explicit background knowledge. Next, please. So these are some of the 2D patterns that's in the data set. Next, please. And this is the 3D patterns in the data set. So this is some of the results. You can check in detail in the poster. Next, please. Oh, thank you.
Your time starts now.
Okay. Hi, everybody. I will now present a brief outline of our work. Next. In our work, we present a new neural-symbolic method for reinforcement learning, which is called state-driven neural logic reinforcement learning. And it is based on another existing neural logic, symbolic method for reinforcement learning. The original method generates a set of logic rules that solve a specific task using a program template, which is a set of hyperparameters, while our work generates the candidate rules directly from the states of the environment. The original algorithm defines differentiable architecture to select the best rule, while our method uses a modified version of this architecture that allows to define multiple rules for each action predicate. Next. Both the tasks, both the algorithm are tested against two main classes of tasks, and our work reaches an overall good performance on one task, while in the other tasks, it fails to reach the end of the training phase, or it...
10 seconds.
Okay. It does not complete at all. It shows encouraging results, however, it has several limitations. Thank you. I'm a bit nervous.
And go.
Hello, my name is NeSy2023, and I'm presenting a poster, Is the Proof length a good indicator for hardness or for reasonable embeddings. Next, please. And reasonable embeddings are recently proposed embeddings for the ALC description logics, which basically tries to solve the problem of concept subsumption using by casting it as a classification problem. Next, please. And so we experimentally showed that the real-world ontologies and quite simple queries are not hard for the reasonable embeddings, and formulas arising from the transformation of quantified Boolean formulas problem are too hard. And the natural question is, what's in the middle? Next, please. So we hypothesized that the amount of work necessary for a typical symbolic reasoner is a good indicator of formula hardness and how hard it will be for the reasonable embeddings. Next, please. And the spoiler alert, yes, that seems to be the case. For more information, please see me at the poster. Thank you.
And go.
Okay. Hello. Can you hear me? Yes. So, next, please. NeSy predictors acquire narrow predicates, also known, wait. Concepts, also known as narrow predicates that comply with the knowledge. Next, please. Does this mean that the learned concepts are interpretable and the model is trustworthy? Next, please. Not always. And that is because of reasoning shortcuts. Sorry for the little joke. So next, please. We show that a reasoning shortcut is an internal solution that achieves optimal prediction, but with an internal semantics on the concepts. So next, please. So come to our poster if you want to know more about them, how to characterize them. And next, please. And also, I will host an official challenge where you can win a beer for giving me one reasoning shortcut. So thank you.
Do you also need industry sponsors? And go.
Hello, my name is Rory Ward, and today I'm going to talk to you about knowledge-guided colorization. Next, please. So basically what it's about is incorporating knowledge graphs with colorization. This is an example knowledge graph that we might use. So if we're colorizing bears or cats, we'd like to be able to look at our knowledge graph and figure out what color they are based on that. Next, please. So this is our architecture. Basically what we do is we have a black and white image. We put that through an image classifier. From there, we figure out that there's a happy bear in the image. We use that as our query to our knowledge graph, which gives us back our color, brown, which we then use to condition our colorizer, giving us our nice brown colorized bear. Next, please. But there's a few issues with this, and three of the main ones I want to maybe have a think about with you is language expressive enough to describe an image faithfully? You know the old saying, an image is worth 1,000 words, but really how many words do you need to describe it? How do we deal with ambiguity? So this is where my little bears down the bottom come in. So if there's a black and white image of a bear, how can you tell if it's a brown bear or a white bear? And the third question is, how do we incorporate visual reasoning into this? So let's say someone is holding an umbrella. Does that mean that the sky is more likely to be gray and overcast and it's likely to rain? Or is it still possible that it can be sunny? So with that, thank you. Next. Yeah.
Okay, thank you. Good evening, everybody. I'm here to present the paper towards invertible semantic preserving embeddings of logical formulae. Next slide, please. So, as the title suggests, the main objective of this work is to find continuous embedding of logical formula, which are in nature discrete objects. And we have a few desiderata for these embeddings. One, of course, the first one is that they are discriminative, meaning that different formula are mapped to different embeddings. But on the other hand, we also want semantic consistencies, meaning that if two formula are semantically similar, we want them to be close in the latent space that we found. And also, most importantly, we want it to be invertible, because once we found the continuous representation for our formula, we want to do some downstream task on here. We want to, for example, optimize it or do semantic search on it, but then we want to go back to another formula. And so what we came up with is a pretty configurable architecture based on the graph variational autoencoder framework for direct acyclic graph, mainly because a formula can be represented by its syntax tree. And so you can give it as input to the architecture and found a latest representation for your formula, and then go back with another graph neural network. Next slide, please. We did a few experiments and also a few ablation studies on these tasks for what's concerned the context of propositional formula, which, despite its simplicity, already poses some challenges, and we found, let's say, promising results. Next slide, please. If you are interested in these topics and you want to know more about it, please come to visit our posters. Thank you.
And go.
Hello, my name is Matt Brown. I'll be talking about trustworthy AI for use in real-world medical imaging applications. Next slide, please. There's been a ton of publications, as you can see, almost 18,000 from 2022 alone. So you might be surprised to learn that AI has almost no use in the real world of medical imaging. Next slide, please. In fact, there's a huge shortage of radiologists in the United States right now, as evidenced by the job postings increasing as we speak. Next slide, please. So we were given a critical task in the ICU to try and use AI to check the position of the endotracheal tube on chest X-ray. This tube has to be 3 to 7 centimeters above the carina. If it's too high or too low, you can injure or kill the patient within minutes. Next slide, please. So we could do this using a deep neural network, which just outputs a simple yes, no on the endotracheal tube position. However, next please. This leaves the physician wondering, how does it decide? Because they know in their head it should be 3 to 7 centimeters above the carina. If it makes an error that seems obvious, they wonder why. And what can they do about it? Do they just throw in more data and hope for the best? Next slide. So the goals of this work was to improve deep neural networks with a knowledge base and machine reasoning for use in medical imaging, to improve the trustworthiness, in particular robustness, error handling, and transparency. And the particular application, as I mentioned, was to check endotracheal tube placement on chest X-ray. Next, please. We developed an open source simple mind architecture that uses multiple agents communicating via a blackboard. Next, please. It translates knowledge onto the blackboard. Next, please. Identifies the next object to find. Next, please. Uses deep neural networks to segment candidate regions. Next, please. And finally, uses reasoning to check against the knowledge to make sure that everything's consistent with the anatomy. Last slide, please. And so I really hope you come by and we can share more details about how we implement these techniques, go through the actual clinical implementation that we've deployed at UCLA and the results of the clinical evaluation, and also share how you can add other deep neural networks and apply simple mind to other problems. Thanks very much.
And thank you to the previous presenters who generously donated 15 seconds to Matt.
Okay. Good afternoon, everyone. I'm David Leake of Indiana University, and I'm going to be presenting a position paper that is joint work with Chris Hammond of Northwestern. The title is Large Language Models Need Symbolic AI. Everyone here is familiar with the amazing things that large language models can do, and also is familiar with the errors, the problems, et cetera. Basically, those have caused a lot of consternation. A lot of people have been very worried about them, and there's been a push to improve large language models in a lot of different ways. The issue with that is that the limitations are more in principle limitations. As Jan-Luc Kuhn said in his wonderful talk today, I think his phrase was, nobody in their right mind would use regressive large language models. And so basically, what we're looking at is, where does that leave us? And the point for us is that large language models are basically symbolic fluency components, and so should be embraced as such. And so we're proposing that AI symbolic models drive them to use them as fluency components, but use the knowledge from the symbolic systems. And so once the little red up there, they need to be driven by symbolic AI. And we'll discuss 2 different ways of potentially doing that, and I look forward to discussing it with you at the poster. Thank you.
and go.
Hello, I'm here to present continual reasoning, non-monotonic reasoning in Neural-Symbolic AI using continual learning. As might be obvious from the title of the paper, the challenge that this paper aims to solve is non-monotonic reasoning. Next. Non-monotonic reasoning is aptly defined by a classic example which is the penguin exception task, in which while we might have a prototype of birds, which we know to be, that are capable of flying, we are later introduced to the concept of a penguin, which is a bird, but unfortunately cannot fly. These kind of reasoning tasks are challenging for symbolic approaches because of conflicting rules or the scale of including all exceptions to the rule, but are even challenging for most neurosymbolic AI approaches. Next, please. So we propose continual reasoning. In principle, continual reasoning is the idea that non-monotonic reasoning tasks, along with classical reasoning tasks, are best addressed by learning to reason in stages. And we apply that and implement an example of that using logic tensor networks on the penguin exception task, in which we take the knowledge base of first-order logic rules, split them into 3 stages, and actually examine how the choice of curriculum and the way that you split those rules into 3 stages affects the results. Next slide, please. Overall, we see that applying continual reasoning improves vastly the results on the penguin exception task and provides a way to address non-monotonic reasoning with neurosymbolic AI models, as well as pairs the result that even when you randomly select how to split the rules into stages, that still leads on average to better results than trying to learn all rules in a single stage. We apply this as well. Is my time already up?
Yeah.
Okay.
Hello, everybody. I am Gabriele Ciravegna, and together with many colleagues from many universities, we created the Logic Explain networks. These are a type of networks that are, next slide please, explainable by design, in the sense that they not only provide classification or in general any kind of learning, such as for example clustering, but also a logic rules for which certain samples belong to that cluster or to that class. We have shown that these kind of networks provide not only the highest accuracy with respect to white box model in general, but they also provide very high explanation accuracy, while being at the same time very consistent with between the logic rule they provide as explanation and the prediction that they provide. And you can also integrate the learning that the logic rules that you already know with the logic rules that you extract to do, for example, tasks such as checking the prediction that your model makes. Next slide, please. The only things that you need is that your input can be treated as a symbolic concept in general, which can be also concept embeddings, for example, which means that you can do it directly on tasks such as text classification or tabular data, but in cases where you have images or graphs as input, you need a concept destructor first. And in output, you have output prediction, but also logic explanation. And if you want to understand better what's in these, come to the poster.
Hi, I'm Eleonora. I'm here to present UVL. Next slide, please. Okay, so let's consider a variational autoencoder trained to predict the label of the image that you see that contains pairs of 2 digits. And the label is the sum of the 2 digits. Now, next slide, please. This task is very straightforward for a VA-like model. But what if we now, next slide, please. We consider different tasks in which, for example, we condition the generation on a difference or a power between the 2 digits instead of the addition. Next slide, please. Now, a VA-like model trained on addition cannot solve this generative task. This is because VA-like models are strongly dependent on the training task and cannot generalize to new ones, please. What we propose to do is to integrate logic programming into variational autoencoders so that the knowledge about how to add digits is provided symbolically by a logic program. Next slide, please. Now, without the need of being retraining, our model can then generalize to other tasks with respect to the training one. Next, please. So we propose VAL, that is the first Neural-Symbolic framework integrating probabilistic logic programming into variational autoencoders. VAL is end-to-end trainable and general purpose. Next, please. It allows to achieve level of task generalization that has never reached before and requires less data than competitors. Next, please. If you want to know more about VAL and also how to generate Mario levels with VAL, have a look at our poster.
Okay, thank you to all the presenters. You did amazingly well. Please do not leave yet. We have still one very crucial program item. But first of all, let's give another hand to the presenters. Like, doing this in 1 minute 45 is actually stressful, and all of you did really well. Woo. Okay, and now I will hand over to Ernesto because there is a NeSy Best Paper Award, which we have to hand out already now because the recipient has to leave the event early for reasons you can ask him about. I'm sure he's happy to tell you once you inquire. Ernesto.
All right. So I'm going to go back a bit. I wanted to create some more suspense on the slides. So yeah, I'm very happy to present the Best Paper Award of NeSy. I mean, it was quite tricky for different reasons, but in the end, like a group of experts or committee of experts, that were in the end Arthur and myself, we decided to give the award to this paper. Like, it's what's wrong with gradient-based complex query answerings to Uns, Sami, and Tarek. And congratulations. Yeah. Do we have Sami? Oh yeah. Because exactly. We need someone to take the photo as well. Yeah, Uns and Sami did a great job. And I'm going on a honeymoon.